On the left side of this diagram, we see the output of standard large language models. They predict the next most likely token, generating linear sequences of code that, lacking structural integrity, eventually collapse under their own weight. On the right, we see deterministic topological synthesis, where logic is bound to a stable, rigid geometry. When you try to run an operating system using probabilistic models, you introduce unacceptable risk. A statistical guessing engine cannot mathematically guarantee logic constraints, prevent memory leaks, or stop hallucinated dependencies from crippling the runtime. This expanding matrix is the automatic lattice. It represents a 24-dimensional logic graph, where code exists not as raw text files, but as proven spatial coordinates. Each of these discrete nodes operates as a specific, mathematically verified atom of logic. True operating system autonomy cannot rely on statistical prediction. It requires the immutability of structural geometry and formal proofs. This brings us to the Omega engine. It operates directly at the root of the system, running as process ID 1, the init process, on a custom-hardened Linux kernel. It commands the entire execution stack. Running as the ancestor of all other processes grants the engine total oversight of the system's logic base. From this root position, it executes autopoiesis, the ability to identify its own logic gaps, compile the missing code atoms, and hot reload its own core functions without needing external permission gates. To understand how this works, we are going to trace the exact chronological life cycle of a single human intent, from the moment a user types a command, through its parsing and shadow compilation, to its final visual rendering on the screen. Tracing this path provides the technical proof of how human desire translates directly into verified, state-safe architecture. The lifecycle begins when a natural language command is ingested by the lattice omega logic model, or LLOM. LLOM immediately discards probabilistic token prediction. Instead, it normalizes the input phrase against a strict static grammar contract known as Category Name Action Entity, or CNAE. Every verb and target is forced into a known canonical format. The normalized grammar instantly transforms into a 48-dimensional vector coordinate, plotting a path through existing logic nodes. This homotopical intent routing calculates the most efficient semantic path, terminating at a visibly empty coordinate where the requested logic should exist. In a sovereign system, human intents materialize as precise routing coordinates within a mathematically proven logic graph. Arriving at that empty coordinate triggers the PL10 emergent whitespace pipeline. The engine recognizes the unoccupied space as a structural logic gap. To fulfill the user's intent, it cues a targeted synthesis operation to build a new code atom that perfectly fits that exact location. Generation is bounded. The lattice is strictly stratified into layers from tier 0 down to tier 7, with dependency arrows only pointing downward. This blocks any attempt by a tier 0 pure node to import stateful operations from tier 3, preventing cyclical deadlocks. A newly generated code atom does not choose its own execution privileges. Its topological location in the tier structure dictates exactly what it can and cannot do. To protect the canonical state of the system from untested code, the newly synthesized candidate atom is immediately quarantined. The compiler packages the candidate, along with its abstract syntax tree dis, into a hermetic, standardized payload. This payload is dispatched to a completely isolated execution runtime, a workspace isolated from the live operating system, for speculative testing.
Here, the system initiates the snowball convergence loop. When the speculative code inevitably fails a compilation or runtime check, the engine does not discard it. Looking at this isolated node, we see how the compiler extracts the exact failure trace. It converts that trace into a measurable geometric arrow, a structural error gradient, which it feeds directly back into the code block to inform the next mutation. The OS relies on controlled isolated failure to physically map the boundaries of successful logic. By applying the error gradient as retrocausal feedback, the compiler forces the candidate atom to physically restructure itself. This loop is governed by the Bonic fixed-point convergence limit. It applies a strict mathematical reduction factor to the variance of the code's state space on every cycle. As the shape pulses, the mathematical contraction compresses the logic. It sheds unnecessary token weight and forces the recursive generation loop to settle into a stable, unmoving state,
eliminating the risk of infinite oscillation. Once stable, a final execution trace against the Lyapunov stability invariant proves the absence of structural decay. The immune gate issues a viable verdict, and the fully proven atom is promoted out of the shadow environment into the canonical DNA shards. Heuristic testing is prone to edge cases. Banach contraction and Lyapunov invariance act as the physical guarantors of system integrity. Pulling our perspective up from the back-end compiler mathematics, the dense 3D node matrix flattens out into the user-facing interface. This is the malleable UI subsystem. It operates as an infinite graphical canvas mapped directly over the underlying topological lattice we just explored. Now we see intent binding in action. The successfully compiled canonical code atom from our shadow loop dynamically mounts itself onto this canvas as an interactive telemetry widget. Navigation relies on a lightweight JavaScript window manager. It continuously translates infinite pan and scroll wheel actions from the user into precise coordinate mapping across the grid. This user interface functions as a live, direct projection of the engine's internal mathematical state. To manage this infinite canvas without causing browser crashes or DOM bloat, the OS relies on fractal level of detail rendering. When the user's zoom scale drops below a threshold of 0.65, the system enters a shallow overview state. In this overview, complex nested nodes collapse. The system displays only opaque, minimalistic status cards to preserve rendering resources. But as the zoom pushes in and the scale factor increases, those cards dissolve to reveal their subdividing data. Pushing the scale factor past 1.35 triggers the deep focus state.
Deep focus unlocks granular visual debugging. As the widget fills our field of view, it renders the real-time abstract syntax tree execution traces and deep architectural metadata directly inside the boundary limits. The visual depth of the UI matches the mathematical depth of the compiler, scaling based entirely on the user's focal coordinate. The life cycle of a sovereign intent is an unbroken chain. It starts with natural language parsing, routes through structural whitespace calculation, optimizes inside a shadow runtime, and culminates in a tangible, interactive fractal widget. This end-to-end pipeline holds together because of strict geometric bounding, tier stratification, and rigorous mathematical convergence theorems enforcing stability at the root of the OS. The Omega engine proves that true software autopoiesis is a deterministic topological inevitability. Probabilistic prediction is obsolete when you can write the code with math.